In the vast tapestry of cosmic history, one moment stands unparalleled: the instant our universe blinked into existence. From galaxies that dance in the night sky to the very air we breathe, everything traces back to this singular event, the Big Bang. But what if we could rewind the universe's clock and glimpse into those first fiery moments? How did a formless, hot soup of particles evolve into the structured cosmos we witness today? Dive with us into an audacious experiment that dares to recreate the beginnings as we grapple with questions that have puzzled humanity for eons. Recreating the dawn of the universe. In the vast expanse of space, the dawn of our universe was heralded by the Big Bang, a cataclysmic event that spewed matter in every direction, laying the foundation for galaxies, stars, and the intricate web of cosmic structures we observe today. But what if we could rewind time, venture into those initial moments, and experience the universe's very first heartbeat? Enter the Little Bang, an audacious experiment aiming to simulate the early universe's conditions on a much smaller, controlled scale. Unlike the Big Bang, which remains an abstract, monumental event in cosmic history, the Little Bang is a tangible, lab-produced phenomenon that physicists have created to emulate the initial stages of the universe. At the Brookhaven National Laboratory, researchers have been using the Relativistic Heavy Ion Collider to create conditions resembling those immediately after the Big Bang. By accelerating two beams of gold nuclei close to the speed of light and then smashing them together, they create a miniaturized version of the Big Bang. This collision gives rise to a hot, dense state of matter known as the quark-gluon plasma, the very soup thought to have existed in the universe's first microseconds. The Little Bang serves as a time machine, albeit on a minuscule scale. The ensuring quark-gluon plasma gives researchers a fleeting yet insightful glimpse into what the universe might have looked like when it was less than a microsecond old. The very fact that scientists can produce, even momentarily, the conditions that are believed to have existed so soon after the universe's birth is nothing short of miraculous. Yet while the Little Bang is indeed a smaller-scale representation, its implications are vast. It holds the keys to some of the most pressing questions in cosmology. How did the primordial soup of quarks and gluons evolve into the atoms and molecules we're familiar with? What forces were at play in the universe's infancy? The Little Bang doesn't just represent a scientific experiment. It embodies humanity's insatiable quest to understand its cosmic origins. As we delve deeper into its intricacies, we get closer to unraveling the mysteries of our universe's earliest moments. Peeking through the cosmic veil. As we gaze into the universe's vast expanse, there remains a hidden epoch, a time shrouded in cosmic mystery immediately following the Big Bang. Our most advanced telescopes can only peer as far back as the cosmic microwave background, leaving an intriguing gap in our understanding. Within this gap, the Relativistic Heavy Ion Collider and its adept companion, the solenoidal tracker, STAR, seek to bridge our knowledge void. Their mission? Explore the intricacies of the quark-gluon plasma, the universe's primordial state. This elusive concoction, composed of elementary particles, quarks and gluons, has never been observed in isolation in nature. Typically, they coexist within more complex structures like protons and neutrons. However, under extreme conditions, such as scorching temperatures, these entities break free, culminating in the quark-gluon plasma. Intriguingly, this plasma behaves not as a gaseous state, but more akin to a fluid, flowing and ebbing in the early universe. With the insights from the collider, scientists aim to unveil the mysteries of this state and, by extension, the universe's nascent moments. A cosmic thermometer. If the Relativistic Heavy Ion Collider serves as our cosmic magnifying glass, then the upsilons it generates are our celestial thermometers, taking the pulse of the universe's fiery infancy. To understand the temperature of the early universe, scientists at Brookhaven embarked on an ingenious experiment. They propelled beams of gold nuclei to nearly light-speed velocities, orchestrating a collision that briefly recreated the quark-gluon plasma's conditions. But why use gold nuclei? Their collisions give birth to upsilons, particles formed from a quark and its antimatter counterpart. These upsilons exist in varied configurations, each with a distinct sensitivity to temperature. By observing how these configurations respond within the quark-gluon plasma, scientists can gauge the plasma's temperature. Think of it as melting different kinds of ice in varying heat levels. The type that melts first indicates a specific temperature range. This innovative approach doesn't just measure heat. The temperature is a gateway to understanding other quark-gluon plasma properties, its density, pressure, and even its viscosity. By charting the behavior of these upsilons, researchers are taking calibrated temperature readings of the universe just moments after its birth, offering a tantalizing glimpse into conditions at the dawn of time. Pioneering experiments and future endeavors. While the endeavors at Brookhaven National Laboratory are groundbreaking, they're not the first of their kind. The Large Hadron Collider at CERN previously ventured into this domain in 2012, plunging deeper into the quark-gluon plasma by harnessing even greater energies. However, Brookhaven's experiments possess a distinct advantage. By studying the plasma at slightly lower energies, they gain invaluable insights into its temperature-sensitive properties, shedding light on its diverse behavioral nuances across different energy spectrums. The recent experiments at Brookhaven have been particularly revelatory. After initiating their gold nuclei collisions, researchers discerned that a significant portion of the upsilons had undergone a transformative melting process, confirming the staggering temperature hypothesis, a realm of heat that surpasses the core of the Sun by nearly 1,000,000 times. But these findings are just the beginning. With an insatiable curiosity to refine their understanding, the STAR team is poised for another expedition into the cosmic abyss. Their arsenal will soon be bolstered by 20 times more data and the introduction of Sphenix, a cutting-edge detector promising even higher precision. As the horizon of our understanding expands, so does our determination to unearth the universe's most profound secrets. The quest to decode the quark-gluon plasma is more alive than ever, marking an exciting era of cosmic exploration. Building a cohesive picture. In the grand tapestry of cosmology, understanding the quark-gluon plasma isn't just about examining a momentary high-temperature state of the early universe. It's a fundamental part of constructing a comprehensive and detailed understanding of our universe's entire timeline. As experiments like those at Brookhaven and CERN shed light on this primordial substance, they provide crucial insights that help piece together a broader narrative. One of the major challenges faced by researchers is harmonizing various experimental findings and theoretical predictions. With every experiment, new data emerges, sometimes aligning with, but often challenging or refining, existing theoretical models. The quark-gluon plasma serves as an illustrative example of this dynamic. Its properties, behavior, and the very conditions under which it forms are elements of a jigsaw puzzle. And each experimental observation is akin to a puzzle piece waiting to find its correct position. In addition to experimental insights, collaborations between physicists, cosmologists, and astrophysicists from around the world have fostered a multidisciplinary approach. By combining knowledge from distinct fields, researchers are enhancing their comprehension of the broader context in which the quark-gluon plasma exists. This synthesis aids in understanding not only the plasma itself, but also its role in the evolution of the universe and its influence on subsequent cosmic phenomena. The ultimate goal for scientists like Ma and the teams at Brookhaven and CERN is to create a cohesive and universally accepted theory that ties together the vast range of observations and experimental results. This would serve as a guidepost for understanding the universe's history, its current state, and potentially its future trajectory. Yet, as researchers inch closer to this unified picture, they also remain humbly aware that the universe in all its vastness and complexity always holds more mysteries in store. Every answer found often paves the way for newer, even more challenging questions. But in the relentless pursuit of knowledge, these challenges are what drive the spirit of discovery ever forward. As we close today's journey into the captivating origins of our universe, it's hard not to be overwhelmed by the sheer magnitude of what's still out there, waiting to be uncovered. Each discovery, every experiment we've delved into, paints a piece of this vast cosmic canvas. And yet the mystery only deepens. What mind-blowing discoveries await us on the horizon? And as we chart these celestial waters, how will these insights transform our view of this grand cosmic dance? Drop your wildest theories, thoughts, and burning questions in the comments section below. If today's adventure resonated with you, drop us a thumbs up. And if you're new here or haven't taken the leap yet, hit that subscribe button and ring the bell for more interstellar voyages with Space Infinity. Remember, the universe is vast, but our quest for knowledge is infinite. Until our next stellar journey, stay curious and keep reaching for the stars.